21.1 degrees Celsius. That is the level reached in late August 2026 by the estimated average sea surface temperature of the global ocean outside the polar regions. The number does not come from a single thermometer. Behind it is an enormous observing system. Satellites circling the planet, drifting buoys in the open sea, measurements collected from ships, and computational systems that combine those observations into a coherent picture. Earth looks blue from space for a reason. More than 70% of its surface is covered by water, and in late August 2026, the average sea surface temperature outside the polar regions reached a new daily maximum in the modern observational record used to monitor the global ocean. But before going any further, one distinction matters. 21.1 degrees does not mean that the entire ocean is 21 degrees. Tropical waters can be far warmer. Higher latitude waters can be dramatically colder. This is an average across an immense area of the planet, roughly between 60 degrees south and 60 degrees north. The polar oceans are not included in this particular widely used indicator, so the number is not an average of every square kilometer of ocean on Earth. And this is where the story becomes more interesting. The global average sea surface temperature outside the polar regions follows a recognizable seasonal cycle. In the modern climate, its primary annual maximum usually occurs around March. Temperatures then decline, before a smaller secondary rise can appear later in the northern hemisphere summer. That makes a record in late August notable for more than its size. It is also unusual because of where it appears on the seasonal curve. In 2026, that curve remained high enough for the late summer rise to push the global value beyond the previous daily maximum. Imagine a line that repeats a broadly familiar rhythm year after year. Individual years move above or below it, but the seasonal pattern remains recognizable. Now imagine the entire line shifting upward. That is closer to what scientists are watching today. So the central question is not simply whether a record was broken. The deeper question is this: why is the ocean carrying and releasing so much heat now, and what could that mean for the atmosphere in the months ahead? To answer that, we have to move from orbit to the surface of the sea, and then much farther down, into a part of the climate system that satellites cannot directly see. First, what do scientists actually mean by sea surface temperature? There is no single instrument measuring the entire ocean. Satellites observe infrared and microwave radiation associated with the uppermost surface. Drifting buoys measure the water directly. Ships provide additional observations. Different instruments see slightly different parts of the surface layer, under different conditions, and with different strengths and limitations. A satellite can cover enormous areas rapidly, but clouds can interfere with some measurements, and the very top skin of the ocean can respond quickly to sunlight, wind, and rainfall. A buoy measures the water directly, but only at one location. Ships add another source of information, continuing a history of ocean temperature measurements that reaches back long before satellites existed. Modern climate monitoring brings these observations together. Some of them are incorporated into systems known as reanalyses. A reanalysis is not a forecast of the future. It is a consistent reconstruction of the state of the climate system, combining observations with the laws of physics and a numerical model to create a continuous picture through space and time. One of the key modern datasets used for daily global comparisons begins in 1979. Against that record, the late August value stands out. The distinction between the polar and non-polar oceans also matters. Around Antarctica and in the Arctic, sea ice changes the surface dramatically through the year. Open water can become ice-covered, and ice can retreat to expose the ocean again. That makes the physical and observational environment different from most of the world's open ocean.
For this reason, one commonly followed global sea surface temperature indicator focuses on the ocean between roughly 60 degrees south and 60 degrees north. That is the domain behind the 21.1 degree figure. But a single record day is only one point on a much longer graph. The global ocean was not cold yesterday and suddenly hot today. The background story has been developing for decades. Since the satellite era began, average sea surface temperatures have risen over the long term, while year-to-year natural variability continues to move temperatures up and down around that trend. The last several years have been especially remarkable. 2023 brought an extraordinary rise in global sea surface temperatures. 2024 remained extremely warm and produced previous daily peaks. 2025 stayed elevated. And now, in 2026, another daily maximum has appeared. That sequence is more informative than any single number. A one-day record does not prove that the climate system has suddenly entered an entirely new regime. Scientists look at persistence. They look at geographic extent. They look at what is happening below the surface, and they ask whether the same signal appears across multiple independent observing systems. This summer, unusual warmth has not been confined to one small patch of ocean. Elevated sea temperatures have appeared across parts of the Pacific, the Atlantic, the Mediterranean, and sections of the Indian Ocean. That brings us to another important distinction: absolute temperature versus temperature anomaly. If scientists say that a region has an anomaly of plus 2 degrees Celsius, they do not mean the water temperature is 2 degrees. They mean it is 2 degrees warmer than the expected average for that location and that time of year. A 2-degree anomaly in the North Atlantic and a 2-degree anomaly in the tropics can therefore represent very different absolute temperatures. Anomalies tell us how unusual the conditions are relative to the local climate. Absolute temperatures tell us how warm the water actually is. Both matter. And in the summer of 2026, marine heat has been distributed unevenly across the planet. Some areas have experienced prolonged marine heat waves. In parts of the Mediterranean, for example, persistent atmospheric warmth, weak winds, reduced upper ocean mixing, and an already elevated ocean background can combine to keep surface waters unusually warm for days or weeks. But another major part of the story is unfolding thousands of kilometers away, across the tropical Pacific. El Niño. Under neutral conditions, easterly trade winds blow across the equatorial Pacific. Those winds help push warm surface water toward the western side of the basin, toward Indonesia and the western Pacific. In the east, near South America, colder water can rise from below through a process called upwelling. That colder water is rich in nutrients, helping support some of the world's most productive marine ecosystems. During El Niño, this balance changes. The trade winds weaken or reorganize. Warm surface water spreads farther east. Upwelling in the eastern Pacific weakens. Sea surface temperatures across the central and eastern tropical Pacific rise above their usual values. And because the tropical Pacific covers an enormous area, the consequences do not remain confined to the ocean. The ocean changes the atmosphere above it. Where warm water shifts, evaporation changes, cloud formation changes, tropical rainfall patterns move, atmospheric pressure patterns adjust. Those changes can then influence circulation far beyond the equatorial Pacific. By August 2026, El Niño was established and continuing to strengthen. In NOAA's August outlook, the probability of a very strong event during the Northern Hemisphere fall and winter of 2026 into 2027 was above 90%. NOAA also estimated roughly a 69% chance that the October to December period could reach a historically strong threshold relative to events observed since 1950. Those are forecasts, not measurements of a peak that has already happened. That distinction is crucial
El Niño develops over months. Ocean temperatures change, trade winds respond, subsurface warm water moves, the atmosphere begins to couple more strongly to the ocean.
Only then do many of the wider global effects become clear. And even if this El Niño becomes exceptionally strong, it will not explain everything happening in the global ocean. El Niño is a natural mode of climate variability. Human-caused global warming is a long-term shift in the planet's energy balance. The two processes can operate at the same time. El Niño redistributes heat between the ocean and atmosphere and can temporarily raise global surface temperatures. But it is now operating on top of a climate system that contains more energy than it did several decades ago. That is why it is misleading to treat El Niño as though it creates all of today's ocean warmth from nothing. The better way to think about the situation is as an overlap. Long-term warming raises the background state. Natural variability moves heat around that warmer system, and sometimes those processes reinforce one another strongly enough to produce new records. But the surface is only the beginning. To understand the full scale of ocean warming, we have to look beneath it. Water has an enormous capacity to store heat. It takes far more energy to warm a kilogram of water by 1 degree than it does to warm the same mass of air. That is one reason the ocean plays such a dominant role in Earth's climate system. Scientists estimate that the ocean absorbs more than 90% of the excess heat accumulating in the climate system as a result of Earth's energy imbalance. The atmosphere is where we experience weather directly, but most of the additional heat is stored in the water below, and that heat is not distributed evenly with depth. The upper tens of meters can respond rapidly to sunlight, wind, clouds, rainfall, and storms. Below that, the upper few hundred meters change more slowly. Deeper still, down toward 2,000 meters and beyond, changes occur on longer timescales. This leads to one of the most important distinctions in the entire story. Sea surface temperature is not the same thing as ocean heat content. Sea surface temperature tells us about the upper boundary of the ocean. Ocean heat content tells us how much thermal energy is stored through a much deeper layer of water. A surface temperature can jump over a few days because winds weaken or skies become clear. It can fall when a storm mixes colder water upward. Ocean heat content changes more slowly. That makes it an essential measure of the longer-term accumulation of energy in the climate system. But measuring the deep ocean is difficult. A satellite can observe the surface. It cannot directly measure the temperature 2,000 meters below. For that, oceanographers rely on instruments in the water itself. One of the most important observing systems is Argo. Thousands of autonomous profiling floats operate across the world's oceans. An Argo float repeatedly changes its buoyancy and moves through the water column. It drifts at depth, descends, then rises toward the surface while measuring temperature and salinity through a vertical profile. Many standard Argo floats profile down to around 2,000 meters. When they reach the surface, they transmit their measurements by satellite. Then the cycle begins again. Before Argo expanded in the early 2000s, measurements of the deep ocean were much more sparse. Research ships could collect extremely valuable profiles, but they could only sample particular routes at particular times. A global network of autonomous floats changed oceanography. Instead of isolated snapshots, scientists gained a much more systematic view of the upper 2 kilometers of the world's oceans. And those measurements show why the surface record cannot be treated as an isolated event. Ocean heat content has been rising over the long term. Even when surface temperatures temporarily fall during periods such as La Niña, the deeper ocean can continue accumulating energy. That is an important point. The surface can cool for a time without the climate system as a whole losing the excess heat accumulated over decades. Energy can be redistributed. It can move vertically. It can move between ocean basins. It can move between the ocean and atmosphere. The surface is the part we see most easily. It is not the whole reservoir.
So what does an unusually warm ocean mean for weather? This is where careful language matters. Start with the physics. Warmer water generally increases the potential for evaporation. A warmer atmosphere can also hold more water vapor. If the atmospheric circulation provides the right conditions, additional moisture can contribute to heavier precipitation. But the phrase, "if the conditions are right," matters. A warm ocean does not automatically create a flood. It does not determine where a storm will form. And it does not tell us exactly how much rain will fall in a particular city. It changes the environment in which weather systems develop. The same caution applies to tropical cyclones. Warm ocean water provides energy that tropical cyclones can use. But sea surface temperature alone does not determine whether a hurricane or typhoon forms, where it travels, or how strong it becomes. Vertical wind shear matters. Atmospheric humidity matters. The structure of the disturbance matters. Large-scale circulation matters. And the temperature of the water below the immediate surface matters. A powerful cyclone mixes the upper ocean. If very warm water extends to greater depth, the storm may continue drawing energy even after mixing begins. If cooler water lies close beneath a thin, warm surface layer, mixing can bring that colder water upward and reduce the available energy. This is one reason ocean heat content can matter for tropical cyclone intensity, not just the temperature of the top few millimeters. And it is also why scientists do not attribute an individual hurricane, flood, or extreme rainfall event to one climate factor simply because the ocean was warm. Specific attribution requires a much more detailed analysis. Another consequence of sustained ocean warmth is the marine heat wave. A marine heat wave is not simply one hot afternoon at the beach. It is a period when ocean temperatures in a particular region remain unusually high relative to the normal seasonal range for long enough to place ecosystems under sustained stress. Duration matters. A brief temperature spike may be survivable for many organisms. Weeks or months of abnormal heat can be very different. Coral reefs are one of the clearest examples. When water remains too warm for too long, corals can expel the symbiotic algae that provide much of their energy and color. The coral turns pale or white. This is coral bleaching. Bleaching does not always mean immediate death. If conditions improve quickly enough, some corals can recover. But prolonged or repeated heat stress raises the risk of mortality. Marine heat waves can also alter plankton communities. Fish can shift toward cooler waters or greater depths. Species distributions can move. Food webs can change. And warmer water physically holds less dissolved oxygen than colder water. Combined with changes in circulation and biological activity, that can worsen low oxygen conditions in some regions. These changes matter far beyond marine biology. Fisheries depend on where commercially important species live. Aquaculture depends on local water conditions. Coastal tourism can depend on healthy reefs. Communities that have relied on the same marine ecosystems for generations may find that familiar species become less common, while others move in. The effects are not identical everywhere. Some regions lose species. Others temporarily gain species arriving from warmer waters. Some fisheries decline. Others shift geographically. The ocean does not respond as one uniform body. It is a connected system filled with regional differences. Ocean warming also contributes to another long-term change: sea level rise. Two separate mechanisms are important here. The first is thermal expansion. When seawater warms, it expands.
The change for any small amount of water is tiny, but spread through an enormous volume of ocean, thermal expansion contributes significantly to global mean sea level rise. The second mechanism is the addition of water that was previously stored on land. Mountain glaciers lose ice. The Greenland ice sheet loses mass. Antarctica contributes additional water as land ice is lost. These processes add water to the ocean. Thermal expansion and land ice loss are physically different, but both raise sea level. Satellite altimeters have measured global sea level since the early 1990s with extraordinary precision. The long-term trend is upward. For coastal communities, even gradual sea level rise can increase the baseline from which storm surges and high tides operate. That can increase the frequency of coastal flooding, accelerate erosion, and contribute to saltwater intrusion into freshwater systems. These are slow changes compared with a hurricane or a flash flood, but slow does not mean unimportant. Now return to the shorter horizon. Autumn and winter 2026. The ocean and atmosphere are continuously exchanging energy. The ocean can be thought of as a vast thermal reservoir. It stores energy over long periods and releases some of it back into the atmosphere through evaporation, sensible heat, radiation, and changes in circulation. As El Niño strengthens, its influence on global atmospheric circulation is expected to become more pronounced. Scientists call the distant connections between tropical Pacific conditions and weather patterns elsewhere teleconnections. They are not guarantees, they are shifts in probability. Historically, El Niño can alter rainfall patterns across parts of North and South America. Australia and portions of Southeast Asia often experience an increased risk of drier conditions during strong events. Parts of South Asia can see changes in monsoon behavior. Different regions of Africa can respond in different ways. The connection to Europe is generally weaker and less direct than in many tropical and subtropical regions. But none of these patterns should be interpreted as a precise forecast for a particular city. A strong El Niño does not tell you what the weather will be on a particular day 3 months from now. It changes the odds, and every El Niño is different. The exact location of the warmest Pacific water matters. The timing matters. The strength of the atmospheric response matters. Interactions with other ocean basins matter. Internal atmospheric variability matters. That is why seasonal forecasts are updated repeatedly. The most likely outcome in August can be refined in September. It can shift again in October. New observations continuously change the picture. Some of the most useful early information comes from below the ocean surface. In the tropical Pacific, scientists watch the thermocline, the transition zone where temperature changes rapidly with depth. Subsurface warm anomalies can travel across the basin before the full signal becomes obvious at the surface. Equatorial observing systems and profiling floats help track that hidden evolution. This is one reason modern El Niño forecasting is not based on a surface map alone. The ocean remembers. Heat stored below the surface can provide clues about what may happen months later. And that brings us to 2027. Changes in the tropical Pacific do not influence global air temperature instantaneously. There is a lag between the development of El Niño and its maximum effect on the global atmosphere, and that lag varies from event to event. A powerful El Niño strengthening in the second half of one year can therefore influence global temperature into the following year. That makes 2027 a year climate scientists will watch closely. If the current El Niño becomes very strong, the potential for exceptionally high global temperatures can increase, but a record cannot be declared in advance. The final outcome will depend on how strong the event actually becomes, how long it lasts, what happens in other ocean basins, and how the atmosphere responds. The correct statement today is not that 2027 will definitely become the hottest year ever measured. It is that a very strong El Niño would increase the potential for another exceptionally warm year, while substantial uncertainty remains. The same caution applies to 2026. The year is not over. Annual rankings can only be determined after all 12 months have been observed. Climate science is strongest when it distinguishes clearly between what has happened, what is likely, and what remains uncertain. And now we can return to the number where this story began. 21.1 degrees Celsius. At the beginning, it was simply a number, a global average, a point on a graph. Now, there is much more behind it. There are satellites circling hundreds of kilometers above Earth. There are drifting buoys moving with the currents. There are ships taking direct measurements. There are autonomous Argo floats repeatedly diving towards 2,000 meters and returning to the surface. There is El Niño reorganizing heat across the tropical Pacific. There are marine heat waves stressing ecosystems. There is a deeper ocean storing an immense quantity of energy that cannot be seen from space. And there is an atmosphere continuously responding to the ocean beneath it. The central story of this record is not a single day. It is not even the fraction of a degree by which one maximum exceeds another. The real question is how persistent this unusual warmth will be, how much energy remains stored below the surface, and how the ocean will redistribute that energy through the climate system over the months ahead. Scientists will answer those questions gradually, one satellite pass at a time, one buoy profile at a time, one monthly update at a time. That is how climate science works. A single record is one point. Thousands of measurements form a curve. Decades of curves reveal a trend. And the trend becomes meaningful only when we understand the physical system underneath it. The story will continue through the autumn as El Niño evolves. It will continue through the winter as its atmospheric influence becomes clearer. And it will continue into 2027, when scientists will be able to see how strongly this event affected global temperature and how quickly the tropical Pacific changes after its peak. We spend most of our lives looking upward to understand the weather. We watch the clouds, we watch the sky, we watch storms approaching on radar and satellites. But much of the energy shaping the climate system is not above us, it is below. At night, seen from orbit, the continents reveal themselves through networks of city lights. The oceans remain mostly dark, quiet, almost featureless from that distance. Yet beneath that darkness lies the largest active reservoir of heat in Earth's climate system. The ocean is not simply responding to climate, it is part of the machinery that creates climate. So if we want to understand what happens next, we cannot look only at the atmosphere. Sometimes the most important signals are hidden beneath the surface, and sometimes the most important answers are found deeper still.